Assalamualaikum and a very good evening to all my lecturers. My name is Haris Moinari with matrix number 190000850 from the groups 20 the Quintets Chemical Engineering 1. My part in this IP project was the separation process part. Thank you.
Assalamualaikum and hello. My name is Aunima Sarah Putri and my ID is 190000748.
Hi, my name is Bhavani Balachandran and I'm going to explain the process modeling simulation part in this integrated project.
Assalamualaikum, my name is Halimatu with the ID number 190000542. My part for this integrated project is reaction engineering, which is manual calculation of sizing reactor.
Hi, Assalamualaikum. My name is Nurul Izzati binti Abdullah and my ID is 190000653 and I'll be explaining about the chapter 2 reaction engineering. So chapter 2 is about reaction engineering. It will cover the type reactor use, operating condition, reactor separator system, strategy, and sizing of the reactor. 2.1 is the type for the reactor use. CSTR reactors have excellent mixing. It performs consistently in a steady state and also commonly used particularly in homogeneous liquid phase flow activities. 2.2 is the analysis and optimization of operational conditions, where methanol is the most ideal alcohol for the biodiesel generation, and methanol has a fast reaction rate with a triglyceride. So next is the description of how the chosen reactor separator system is designed to meet biodiesel production. The transesterification reaction is a reversible reaction in which the reactants are mixed. Raw biodiesel and raw glycerol are the end products. The reaction of the triglyceride with methanol is represented by the general equation. So let's moving on to the possible side reaction that might take place. So the first one is saponification of free fatty acids, the chemical breakdown of lipids which are not easily soluble in the aqueous solution. Furthermore, it is important for the cleansing lipids that are involved in process that include cell development and processing. The second one is esterification of free fatty acid with methanol. Ester forms when a fatty acid and alcohol are combined. It also generated when the alcohol component is glycerol, might be monoglycerides, diglycerides, and triglycerides.
This is 2.4, the strategy to maximize the selectivity and yield of biodiesel and maximize the site reaction. So we come up with the three strategies. So the first strategy is time taken for the reaction. The amount of time allowed for esterification is critical in making high quality of biodiesel with a high yield. Using a basic catalyst like sodium hydroxide, the reaction normally occurs quickly at first and subsequently slow as the more diesel is created and few material to react. So because the reaction is slow beyond the point, so it normally recommended for the reaction to run 1.5 to 2 hours to optimum yield and quality. The second strategy is the type of alcohol used. For the maximum yield, however, more alcohol is usually used, and if there's too much of alcohol, it will be difficulty to separating the biodiesel from the glycerol because glycerol become more soluble in biodiesel. So the type of alcohol used can also have the effect on overall effectiveness of biodiesel production. So typically, methanol is used because it's cheaper and also to prevent the separation of the biodiesel and glycerol production. So lastly is the catalyst. The type of the basic catalyst like sodium and potassium hydroxide are good at increasing the rate of reaction and producing biodiesel. Another option is sodium metallate, also known as the sodium methoxide solution already dissolved in the methanol. This solution can produce a high yield and require less catalyst and improve the safety due to lower exposure to the corrosive. Next is 2.5, the sizing of the reactor. So there's a few assumptions are made. So first, continuous stir tank reactor, CSTR, is chosen for this reaction. First order reaction with no change in volumetric flow rate. There's a steady state reaction, and we assume that it is well mixed and perfect mixing occurred. No special variation and close boundaries. So here is some of the equation that involve in the manual calculation of reactor sizing. There's a 5-step to calculate the reactor sizing. So first step is the mole balance, and the second step is the rate law, and we assume that there's a elementary reaction and B in excess B, which is methanol, and we are using our Henne's equation to find the value of K. And then next step 3 is stoichiometry table, and step 4 is combine the which is combine the equation from the step 1 and step 3. And then the last step evaluation, and in this step we're going to find the value, the formula of the volume, and we proceed with finding the volume for both CSTR, B1 and B2.
Let's look into the process modeling simulation part. It is generally a reactive system and flows in steady state throughout the process. The rate law for this reaction follows the elementary reaction, where methanol is excess in the reaction acid flows pseudo-order reaction as well. In this simulation, the catalyst used was sodium hydroxide, and for the assumptions are the suggested reactors are cylindrical in shape with constant volume. Reaction is highly isothermic and are perfectly mixed. The overall heat transfer coefficient is assumed to be constant, negligible vapor pressure. The liquid density is constant throughout the process. Next, for the mathematical model, we begin with the rate law, mass balance, component balance for tripalmethane, methanol, methylpalmethane, as well as for glycerol in each reactor. Since we are using CSTR in series with same volume, so the mathematical model is the same for both CSTR. So basically all this represents the component balance for each reactant. In our case, A is tripalmethane, B is methanol, C refers to methylpalmethane and glycerol. These equations are the same to second CSTR. This equation represents the energy balance for CSTR1, which is an exothermic. We assume there is no work done, so after the derivations, the final equations looks as this. Moreover, this is our biodiesel plant design that we have simulated using symmetry. The feed contains tripalmethane, methanol, and sodium hydroxide as catalysts. The temperature and pressure used was 60 degrees Celsius and 400 kPa with feed flow rate of 70 kmol per hour. The design consists of mixer, heat exchanger, CSTR, and cooler. A process calculator was used to study the conversion of our reactor. Apart from that, throughout the sensitivity analysis on the reactor performances, we noticed that the first two graphs shows volumetric flow rate of outlet increases when there is an increase on the temperature and mole composition of tripalmethane, whereas the last graph refers to feed mole flow rate adjusts volumetric flow rate of outlet. Through the simulation, we know that there is a percentage error that we can conclude from the manual calculation, which is 98%. This is due to the feed conditions does not applicable for this reaction, which causes the conversion to be zero and might be because of human error, such as applying different flow rate for the feed. So that's all from me. Thank you.
Alright, next chapter is chapter 4, separation process. We have two types of separators that we have used during the integrated project, which is centrifugal compact separator CCS, as well as falling film evaporator. Centrifugal compact separator CCS is a piece of equipment which uses centrifugal force to operate its process. The centrifugal force is proportional to the rotational speed, mass and radius of the spinning body, in this case 8,000 revolutions per minute, and the mass of the centrifuge. The denser elements will flow to the outside of the inner axis of a centrifuge, leaving the less dense materials closer to the center. The biodiesel is a less dense material than water as well as methanol and the other materials, therefore it will stay in the center, while the unwanted material will spill over to the edge and be discarded, while the biodiesel will be collected. There were several challenges as well as strategies faced during the biodiesel production planning phase of our IP project. The first challenge was the CCS having a high operational and maintenance cost, which can be solved by installing a passive idle motor which reduces energy consumption by conserving the inertia of the spinning centrifuge. Secondly, the vibrations from the centrifuge may disrupt process flow or damage surrounding equipment, and this problem can be solved by mounting the CCS on a separate platform which is secured to the ground. In terms of strategies, the recycling of heat energy from the CSTR into the water heated sleeves, which preheat the material feed before entering CCS, was done to conserve energy as well as reduce operational cost. Last but not least, the strategy to optimize the amount of methanol which can be used as a catalyst within the trans-esterification process was kept at an ideal ratio of 6 parts to 1 in terms of 6 parts oil to 1 part of methanol.
Hello, this is Auni and I will be presenting on the proposed separation unit. So evaporator is used as a separation unit in this process as we aim to achieve quality biodiesel due to the need to remove water vapor. An evaporator is a device used in the process of converting a chemical material such as water from its liquid form to its gaseous form, vapor. In the process, the liquid is evaporated or vaporized into a gas form of the targeted ingredient. Next would be proposed separation technique, and the proposed separation technique used would be evaporation. So evaporation is the process of removing a solvent as vapor from a solution, slurry, or solid suspension in a liquid. The goal is to concentrate a non-volatile solute from a solvent such as organic compound, inorganic salt, acid, or base. In the operation of an evaporator, evaporation is stopped before the solute begins to precipitate. In this case, evaporation is used to remove water as vapor from biodiesel so that concentrated biodiesel will be achieved at the end. Moving on, the proposed separation type would be falling film evaporator. So, the usage of a falling film evaporator as a high concentrator with very low boiling pressure enables final concentration of up to 99.8% to be achieved. A falling film evaporator is a type of industrial device used to concentrate solutions, particularly those containing heat-sensitive components. The liquid is fed at the top of the tubes in a vertical tube bundle in a falling film evaporator. The liquid is allowed to flow as a film down the inner wall of the tubes. The solvent vaporizes and the concentration progressively increases as the liquid passes through the tubes. At the bottom of the tube, vapor and liquid are normally separated and the thick liquor is extracted. A pump located beneath the vapor-liquid separator circulates evaporator liquid through the tubes. Next, for the falling film evaporator material, we propose to use aluminium due to its lightweight, corrosion resistant, and good thermal conductivity. And for the falling film evaporator configuration, the falling film evaporator is a form of vertically oriented shell and tube heat exchanger used to separate two or more liquids with differing boiling points. Moving on with the manual calculation, and to start off the calculation, we have to put our assumption. Our assumption is as stated in the slide.